All right, welcome. So I'm going to use this time to go over all the stuff that we've talked about so far in terms of series. Okay, I don't want to make this too long of a video. I want to make it somewhat short. It's March 18th right now. I meet with you guys on March 19th for the first time, and I want to make sure that I put something out there that you're going to be able to see and can go back to, rewind if you want, and make sure that you remember everything that has taken place up until this point. So first of all, remember, I started a little bit deeper in the series unit than I usually start, and I started with power series, okay? So this is where I started, and it's obviously not the first section in Rogowski's book because I felt like I needed to at least get to a bit of the tougher stuff while I had you live. You know, knowing that this was potentially coming, and now here we are. So power series, I want you to, first of all, recall where this came from, right? So in Algebra 2 and in pre-calc, you dealt with different infinite sequences. Well, first of all, finite sequences, and then infinite sequences, and then finite series, where you found the partial sum, and then infinite series. And one of the infinite series that you learned was the geometric series. So for a geometric series, we have some common ratio. So, you know, in general, what we have is, let's say, some sum as n goes from 0 to infinity of something like r to the nth power. Okay, that's r raised to the nth power. And so let's plug in different values of n in for this. So when n is equal to 0, this is r to the 0th power, which is just going to be 1. When n is equal to 1, we have r to the first power, which is just r plus r squared plus r cubed plus dot, 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 and it goes from there, right? So for this, looking at every term, right, every term going to the next, going to the next, going to the next, we multiply by the same value. So we multiply by, in this case, r, in this case, r, in this case, r. And that's going to have a common value that you multiply each term by to get to the next. Now, the reason why it's called r is because it's really a common ratio. When we look at, so this guy could be, let's say, a sub 0. So when n is equal to 0, right, that's what we have. That's that term. This is a sub 1. This would be a sub 2. But if we take any term divided by the term that precedes it, we're going to get that value r. So that's what that means. It's a common ratio of any term divided by the term that precedes it. And that's what r is. So in this case, you take, let's say, I don't know, r cubed divided by r squared, and you get r, right? So that's the common ratio. So that's a little bit about a geometric series. And what we learned, or what you learned way back taking this with whomever for Algebra 2 and pre-calc, is that a geometric series will converge only if r is in between -1 and 1. So we can say that absolute value of r less than 1, or -1 less than r less than 1. Okay, so we have that this converges only if the common ratio is in between -1 and 1. And it would converge to, so and converges to the first term divided by 1 minus that common ratio. So that's what it converges to. Now, in this example that I have, the first term happens to be 1, so that'd be 1 divided by 1 minus, and then I just have a general geometric series, so I just have r, but that might be like 1/2 or 1/4 or, you know, -2/3, whatever that is. As long as that r value is in between -1 and 1, the infinite geometric series will converge, and it converges to the first term divided by 1 minus the common ratio. Okay, good. Now, we take that and we think about that if we had a function, so we start with this, the summation is n goes from 0 to infinity of r sub n, but we say, what if that r was a variable? Let's call it x. Well, then we would have a function. So we would say f of x is equal to the summation as n goes from 0 to infinity of not r to the n, but let's call it x to the n. Well, this is when n is equal to 0, we have x to the 0th, which is just 1, plus x squared, plus x cubed, plus dot, 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 right? So it's the same thing, only instead of us having an r in there, we have x. So we have a variable that might vary a little bit, right? Hopefully between -1 and 1, because that would give us that this guy converges. So what would that converge to? Well, this is just, we know this converges to the first term divided by 1 minus the common ratio. Well, the common ratio in this case is just x. And so we have, this is true only if, now remember x takes the place of our common ratio, so only if the opposite value of x is less than 1 or -1 less than x less than 1, okay? So this is an interesting thing that I have here. I have that 1 over 1 minus x is exactly equal to this summation as n goes from 0 to infinity of x to the n, which is exactly equal to 1 plus x squared plus x cubed. Let's write a few more terms right on here. And again, it's only if this is true, right? Only if we have an x bar that's in between -1 and 1, but it's weird because we have this rational expression, 1 over 1 minus x is exactly equal to this series that looks like a polynomial, only it doesn't have a finite number of terms. It has an infinite number of terms, right? This 1 plus x squared plus x cubed plus x to the 4th, and then it continues on indefinitely. It never ends, right? And we see that because n goes from 0 to infinity. So that's weird to think about, that this rational expression or function, let's call it, this rational function can be written like this infinite polynomial. And that's where we get a little bit confused, but it does make sense because what we know from geometric series. Okay, then what we said is, okay, for this is what we are going to call a power series. So it is a series. A power series is basically, in just informal way of describing it, is a power series is basically like a polynomial, but with infinitely many terms. It doesn't end after, let's say, the degree 5, the term all the way up through degree 5, but it continues on forever. So that is a power series. It's only raised to powers all the way through. So if we were to try to define what a power series is, we would say, so I should say for power series, we would say this function f of x is equal to the summation as n goes from 0 to infinity. And now this is just one example of a power series right here. But let's say that the coefficients might even vary, right? So I'm going to say a sub n times quantity x minus c raised to the nth power. So if I plug in different values of n for this, I have a sub 0 times quantity x minus c to the 0th power, which is just 1, plus a sub 1 times x minus c to the 1st power, plus a sub 2 times quantity x minus c to the 2nd power, plus, and you see what's happening there, it's going to continue on forever, all right? So this is a power series. And we say it is centered at x equals c. So this power series is centered at x equals c. So you remember I said only if this were true does it converge, and only if the common ratio is in between -1 and 1 will it converge. Well, for this power series that I have here, oops, I took that and moved it down a little bit, I guess. So for this power series that I have here, I'm going to say this isn't true for all values of x. So I want to say, okay, only converges if, and now I'm going to have some number here is less than x is less than some other number here, right? So it's only going to converge if x is in between some value and another value. But how do I even come up with those values, right? Before it was just -1 and 1. But now that the coefficient is changing from term to term, it's going to be a little bit more than that, okay? Well, if we think about where this is centered, on a number line, right? So we said it's centered at C. So let's over here just draw like a number line. And let's have that this guy is centered at, at C. Well, what I'm saying is I can go over a certain distance, let's call that R, on each side of C. And I know that my power series will converge on that interval, or we're going to call it capital R for the radius of convergence, all right? And so if, this is C right here in the center, and I go over and I add R to that, then this becomes C plus R. And over here, this becomes C minus R, because from where I was centered at C, I go and I subtract R from that. So it's really going to be from this C minus R to C plus R. And then another thing that we're going to see is I might have to possibly include those endpoints. That's going to be for another day. I haven't gotten into that yet. This is just a review of everything that I've talked about up until this point, and I haven't talked about that yet. So I'm going to leave that for another day, but just know that's coming to discuss what happens at those endpoints, okay? So anyway, so far that's what we have. And like I said, R, this capital R, is the radius of convergence. So radius of convergence, okay? That's what we call that. So in order to find the radius of convergence, I taught the ratio test, and that's the only test that I've discussed up until this point. There are other tests, and I've shown you on my website where those, the test worksheet is for a series. But let's just remind you a little bit of the ratio test. So the ratio test basically says, as long as the limit as n approaches infinity of the absolute value of, let's say, the next term divided by the previous term, so a sub n plus 1 divided by a sub n is going to be less than 1, then the series will converge. And again, this does not take into account the endpoints, but like I said, we'll get to that later. So basically, this is the ratio test. I went through an example in class. I'm going to go over another example. In fact, let's do one right now. Let's go to our textbook and let's get an example of using the ratio test. Here we go. Get ready for your picture. Ready for it? There it goes. All right, so we have this series, right? The summation as n goes from 0 to infinity of x to the n over 2 to the n And I want to find out where this guy converges. So I'm going to look at, I'll even write it, look at the limit as n approaches infinity of the absolute value of the n plus first term. So all I'm doing is I'm replacing the n's with n plus 1. So that's x to the n plus 1 over 2 to the n plus 1 divided by a sub n, right? So that's just going to be x to the n over 2 to the n. And now I am going to see where this thing is less than 1 in order to guarantee convergence, okay? So this yields that the limit as n approaches infinity of the absolute value, okay, x to the n plus 1 is also known as x times x to the n, divided by 2 to the n plus 1 is known as 2 times 2 to the n. Divided by a fraction is the same as multiplying by its reciprocal, so this is times 2 to the n over x to the n. And this thing has to be less than 1 in order to guarantee convergence. Well, I could cancel out those x to the n's. I could cancel out those 2 to the n's. And so then I have that this limit as n approaches infinity of the absolute value of x over 2 is less than 1. Well, here there are no n's left, so this limit as n approaches infinity doesn't really do anything, right? And really, I could bring out that 2 in the denominator outside of the absolute value mark, so this is 1/2 times the absolute value of x is less than 1, which yields that absolute value of x is less than 2, right? By multiplying both sides by 2. So here, this gives me the radius of convergence is 2. Now, going back up to this, if you notice right here, this is just x to the n. So it's not x minus 4 to the n or, x plus 1 to the n or anything like that. But those guys would be centered at a different c value. Whereas just x to the n is the same as x minus 0 to the n, which tells me that this thing is centered at 0. So if it's centered at 0, and I have that this value now is 2, that means that I have to go 2 units to the left and 2 units to the right. And so I'm going to have -2 to 2 is my initial interval of convergence. And like I said, maybe I'll discuss a little bit about the endpoints right now. But so the radius of convergence, if they just asked for the radius of convergence, I'd say r equals 2. Done, right? But for the interval of convergence, I know it's going to be from -2 to 2, but do I include the -2? Do I exclude it? And the same for the +2. So I don't know. Well, let's go up to this really quickly. And let's say, what if x were equal to -2? What would this series look like? Okay, well, I just had x to the n over 2 to the n. So if x equals -2, it would look like this. The summation as n goes from 0 to infinity of x to the n over 2 to the n, right? Well, this just looks like the summation as n goes from 0 to infinity of -2 over 2, all raised to the n power. But -2 over 2 is just -1 to the n power. So what does this look like? This looks like, let's write out the first few terms. When n is equal to 0, I have 1 plus -1, also known as -1, plus 1 minus 1, plus 1 minus 1, plus 1. Does this converge? Well, no, right? That sum is 1 and then back to 0 because you're adding -1 to 1, so that's 0. And then you add 1, so it's back up to 1, and then 0. Then 1 to 0. Does it go to 1 real value? No, it doesn't. So this thing would diverge. So for this left-hand endpoint, I would not include -2 because that does not make my series converge. Let's try 2. So if x equals 2, I must have said something to Siri because she went on. If x is equal to 2, right, I'm going to have the summation as n goes from 0 to infinity of 2 to the n over 2 to the n, which is just the same as the summation as n goes from 0 to infinity of 1, which looks like what? When n is equal to 0, I have 1 plus 1 plus 1 plus 1 plus 1. Does that converge to a real value? No, it does not, right? Because if you keep adding 1 infinitely many times, that diverges to infinity. And so this guy also diverges, which means that I should not include 2 either. So I already knew that my radius of convergence was 2. Now I know my interval of convergence is from -2 to 2 exclusive, meaning you exclude -2 and you exclude 2. A little note here, there will be intervals of convergence where, you know, one of them is included and the other is excluded, where they're both excluded like this one, or where they're both included. And you need the other tests that I kind of skipped to get us to power series in order to really dive into that. But hopefully this is a little bit of a preview for that. Anyway, so that's where we are so far. And then what I talked about was, okay, if we know that 1 over 1 minus x is equal to the summation as n goes from 0 to infinity of x to the n, let's look at, well, example 4 from the book was so this is example 4 from the book, and it just says, what about 1 over 1 minus 2x? What's that equal to? Well, all that we're doing here is we're replacing that x right here, this guy that was right there, with now a 2x. So this inside, so I had blue, sorry. This is the summation as n goes from 0 to infinity of 2x raised to the n power, also known as the summation as n goes from 0 to infinity of 2 to the n times x to the n. Now, do you see how this right here is like the coefficient part like I was talking about before? If not, rewind the video later and check that out. That's like the coefficient part that's changing every term. And this right there is like the power part. So that's a variable that has a degree attached to it. And it's going to start off x to the 0th, x to the 1st, x to the 2nd. But the coefficients are now going to be 2 to the n. So it's 2 to the 0th, which is 1, 2 to the 1st, 2 to the 2nd, 2 to the 3rd. And so this is going to look like when n is equal to 1, I have 1. When n is, when n is equal to 0, I have 1. When n is equal to 1, I have 2x. When n is equal to 2, I have 4x squared. When n is equal to 3, I have 8x cubed plus ... And it's going to continue on indefinitely, okay? We could use the ratio test to determine the interval of convergence or radius of convergence, but they kind of tell us in example 4 that this is going to be true for absolute value of x less than 1/2. Okay, cool. So that's example 4. I think we also did another one. I'm going to do example 5 for you next. Example 5 has 1 over 2 plus x squared. Okay, something like that. Well, it has to be 1 over 1 minus something. It has to. In order for us to do this, that's what it needs to look like. So what I'm going to do is I'm going to factor out a 2 from the denominator. So I already have 1 over, so that's good. But over here, I'm going to factor out a 2, and I have 1 plus x squared over 2, like that. So that's better, but it's still plus, and it's not minus. So what I'm going to say is, I'm going to say, well, this is the same as, going down here, this is the same as 1/2 times 1 over 1 minus quantity negative x squared over 2. Do you see why I'm doing that? Because it has to look like 1 over 1 minus something. Now, me having that 1/2 out in front that's just multiplying it, that's fine. I'm just going to deal with the 1 over 1 minus something as my summation, and I'll have the 1/2 out in front. So let me show you what that's going to look like. This looks like 1/2 times the summation as n goes from 0 to infinity of something to the n power. What's that something? Well, it's going to be whatever's inside there is going to go right there. So what is that? Negative x squared over 2. So I wouldn't leave it like this because that's a little bit sloppy in terms of the notation. So let's keep working with this a little bit. So I have that this is equal to 1/2 times the summation as n goes from 0 to infinity of. Okay, that negative that's out in front of the x squared raised to the n power is the same as negative 1 to the n. That's going to make it alternating. I think I showed you something like that in class. X squared to the n is also known as x to the 2n. Divided by, and then the denominator 2 raised to the n power is just 2 to the n. Now, the last thing I would do is, well, heck, if this guy's out in front, let's multiply that guy in. Don't worry, it's not hard. It just ends up being the summation as n goes from 0 to infinity of, I'm multiplying the whole numerator up here by this numerator right there. Well, that's just by 1, meaning I'm not changing the numerator. So that's just negative 1 to the n times x to the 2n divided by, and now I'm multiplying this whole denominator here by this whole denominator there. Well, what's 2 times 2 to the n? 2 to the n plus 1. And this is the way I would write it. So let's go back and say, wait, what did I start with again? Oh yeah, 1 over 2 plus x squared. So 1 over 2 plus x squared is exactly equal to the summation as n goes from 0 to infinity of negative 1 to the n times x to the 2n over 2 to the n plus 1. Not always, but on some interval of convergence. I'll let you do that on your own. I want to keep going because I know this is already getting longer than I kind of intended, but so that's pretty good. That's an example of, you know, manipulating the initial function that they give you so that you can make it look like some constant times 1 over 1 minus something else, and then use what we know about our initial power series that we discussed. Okay, cool. So we're moving along, and now we say, what about something like number 6? So let me go to the book and we'll get number 6 from the book, or example 6, I should say. Ready for it? Let's hear it. And go. There you go. All right. So, we want to find a power series for that guy. Well, we can't make that into 1 over just 1 minus something because of that squared term that's in there. So this is when we try to relate this to the 1 over 1 minus x by either differentiating or anti-differentiating this guy. So let me approach it this way. What if I take this? I know that this is equal to the summation as n goes from 0 to infinity of x to the n, right? That's my initial power series. So that's 1 plus x squared plus whatever. So now, what's the derivative? What if I were to take this guy and differentiate with respect to x? What would I get? Well, you tell me, right? This guy would look something like 1 minus x to the negative first power. So what's its derivative? Well, negative 1 times quantity 1 minus x to the negative second power times negative 1 because of the chain rule, right? So I'm just going to be left with 1 over quantity 1 minus x squared, right? Because again, the derivative of what I have here written in black is -1 times quantity 1 minus x to the -2nd times -1. Those negative ones cancel out, and I'm left with 1 minus x to the -2nd, also known as 1 over quantity 1 minus x squared. So knowing that, all I have to do is differentiate this whole thing with respect to x. So let's differentiate that with respect to x. And what would I get? Well, again, this just looks like the summation as n goes from 0 to infinity of. Okay, when I multiply that power down in front, right, because x to the anything, the derivative is that anything times x, that anything minus 1, right? So this is going to be n times x to the n minus first power. Do y'all see that? So all I'm doing is I'm differentiating that whole sum, that whole summation. Now, some of you are saying, yeah, but if n starts at 0, right? My index n starts at 0. When I start at 0 and I plug in 0 for n, what happens to that first term? It's 0 anyway. So I don't need that. So I really could say, oh, this could start at n equals 1. And that's what we would have, okay? Again, if we were to look at this guy and differentiate with respect to x, so there's like term by term differentiation, what's the derivative of 1? 0. What's the derivative of x? 1. 2x, right? If this were, you know, x cubed, this guy would be plus 3x squared plus this guy would be 4x cubed plus dot, 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 right? And that's exactly what I would get. Try plugging in different values of n starting at 1 into what I have written there in the summation notation for blue. It's the same thing. So that's how we can approach that. Cool. I hope that's a good little review. The other thing that it says before I leave you, and then I'm going to try to upload this. The other thing that it says is when we do term by term differentiation, right? Then that radius of convergence is going to remain the same, whatever it is that you differentiated from. So let me go back to this guy. Here, let me do this. I'm gonna bring you back over here. Right? So what it says is, these series have the same radius of convergence r. So if you read through this, when you look back at this, I started with my initial guy, which is 1 over 1 minus x, right? 1 over 1 minus x, we know has a radius of convergence of 1. So therefore, I can tell you this will also have a radius of convergence of 1. Now, you could do that or find that by doing the ratio test still, but you don't need to because you differentiated to get this, okay? All right, I hope that helps. I know this is a lot, especially if you were not in class the last few days of last week, but I wanted to do this to catch you up so that when we meet tomorrow, I could hopefully answer a few questions, but then move on. The homework assignment was page 589, 1 through 8. I want you to do that, but don't worry about the endpoints. Any problem that says, and find the endpoints, just ignore the endpoint part of it, but do everything else. All right? Best of luck. I hope this made sense and was helpful. I'm going to post this to my YouTube account and also on my website. All right. I'll see you tomorrow.